Ma'am, this option is not there, ma'am.
Option is there. ನಾನು ಒತ್ತುದ್ರದು ಆಗ್ತಾ ಇಲ್ಲ.
Ma'am, it is recording now.
Yes, ma'am.
Recording.
Started. Yes, ma'am.
Yeah. Please, Mohit Kumar and Pratiksha and then Nitin Priyadashini, please start today a third day webinar on matrices in engineering. Okay, over to Mohit Kumar.
Good evening, everyone. So today we will be presenting on matrices in engineering. So Pratiksha was supposed to start. So actually she is stuck in a hackathon. So I have recorded her part. So first I will play her part. Do let me know if you can hear her voice or not. Is her voice audible?
No, voice is not audible.
Now?
No?
Yes, it is audible, ma'am.
Audible?
Okay.
But yeah.
Okay, I will play.
But I'm not audible. That's why. Okay. Gunamati is audible?
Yes, ma'am. When he asked, he was audible, ma'am.
No.
That's
Okay.
what is asking. Yes, ma'am.
Okay.
You can start, ma'am. If it is not clear, I'll inform you.
Ma'am, actually, this is a recorder of Pratiksha. Is her voice audible? Pratiksha's voice.
You're talking about our voice. No. First, you need to enable allow system audio.
Okay.
Only your voice is audible. In the presentation, first enable allow system audio.
Couldn't find that option, ma'am. Can you help me with where is it?
So when you start sharing the content, right?
Okay, ma'am. Sure, I will share again.
Yeah.
Okay, here.
When you start sharing the content, then you will get an option.
Okay.
The electric circuit.
Is it audible now, ma'am?
Problems related to the
Yes.
quantum mechanics.
Yeah.
And
Put a little bit voice loud.
You
Okay.
can mute yourself, only your background voice will not come. So only the system audio will be audible. Have you played now?
also optics.
Make it little more voice.
I'm
Yes, ma'am.
I'm here with my teammates
Yeah.
Nitin
Note this
Priyadashi
point.
and Mohit Kumar Manani. So we are here on the webinar on topic matrices in engineering. So we all know that matrices has been affecting and it is been playing a major role in the life of an engineer. So there are many applications about the matrices that have been in engineering. So many such as solving physical related application and problems related to electric circuit and problems related to the quantum mechanics and also optics. And with the help of this matrices, calculation of the battery power outputs and resistors and conversion of electric energy to the another form of energy also can be done. So and also the one of the example that what I am be explaining is application regarding the springs and related to spring and masses. So for this presentation, I'm considering the two example of two spring. So here one of the spring which is fixed end at the both of the ends, and another spring in which the one of the spring is connected to a fixed end and the other one has a free end. So as we can see here, the spring which has two fixed end has, so we have considered four springs for it, for which the three masses it has been represented by M1, M2 and as well as M3. So the forces that has been acting on spring by the masses M1, M2, M3 are Y1, Y2, Y3 and as well as Y4 upon the four springs. Similarly like that, we have another spring which has a fixed end and as well as a free end, for which we are considering the three springs, and the tension that has been acting upon the upon by the three masses M1, M2, M3 are Y1, Y2 and as well as Y3. So since the tension that has been acting at upon towards the downwards, since the acting force are acting downwards, we will be considering it as positive. So whatever the moment that acts upon downwards is considered as positive, and the moment that acts upon upwards considered as negative. Hence the compression will be taken as negative here, as the force has been acting upon a spring for the mass m1, m2 and m3. So the Hooke's law will be considered taken as considered here. So the time for the tension Y and the spring constant C for a spring, the Hooke's law can be derived can be stated as Y is equal to C into E, where Y is the stretching force and C is the spring constant of the respective spring, and E is the stretching distance that is been acting upon the each spring. So the main objective of our webinar about this application is that we are supposed to convert the spring equation y is equal to c into e into a vector form, so that we could perform a calculation in the form of matrices. The vector form could be as ku is equal to f. So where k is the stiffness matrix which we would be calculating here, and the u is the elongation which is obtained from the given problem, and f is the natural force that has been acting. So the natural force here is in gravity, so hence the value of f is will be equal to mg for each spring. So f is equal to m1 g1, m2 g2 and m3 g3. So in order for derivation, so we have considered four parameters. So one is the u, that is the moment that has been acting upon the spring, and is the elongation that is been forced by the spring upon acting of the masses upon the spring, and y is the internal forces. Internal forces will be calculated by using the obtained values, and f is the external force, that is the gravity that has been acting upon it. So here the brief model of the mathematical expression we could see here. The moment of the spring, for which the values will be given from the matrix of A, that can be calculated as E is equal to A and A multiplied by U, and the value or the elongation that we have obtained will, when it has been multiplied with the spring constant for the respective spring, the value C into E will be the internal force that we obtain, that is y is equal to C into E. And when the C into E will be multiplied with the transpose of the matrix, we'll get the external force, that is F, that has been acting upon the spring. So by using these three equations, we'll be calculating uh, the vector form of the value. And so the elongation, since we are considering four springs, the elongation E can be generalized by using the formula E1 is equal to U1 minus UI minus 1. Since the spring which is connected at the fixed end will be 0, as there will be no elongation happened at the 0th stage. So E1 is equal to U1, and similarly by replacing the value of 2, E2 will be equal to U2 minus U1, and similarly E3, and also for the E4. So whatever the value we obtain for E1 and E2, E3 and E4 will be represented in the form of the matrices. So as the value E is equal to AU we have obtained from the previous slide here. So we'll be writing it in the form of matrix. So the matrix we can see here, that will be 1 0 0 minus 1 1 0 0 minus 1 1 will be multiplied with the u1 u2 and as well as the u3. Similarly, by applying the Hooke's law, so Hooke's law will be applied for each string, as mass m1 will be acting upon the respective masses will be applying upon the respective spring. The Hooke's law will be, the value for the Hooke's law will be y1 is equal to c1 into e1. Similarly, it follows for the all the four springs, The same way, the value whatever we have obtained will be representing it in the form of the matrices, that is y1, y2, y3 and as well as y4 will be equal to C1. The other white spaces are the 0 value, and another row matrix with the values E1, E2 and E3 and as E4. The values of E is equal to AU, and also the Hooke's law y is equal to C into A will be combining it to get the value for the tension force, that is y is equal to CA and U. And also from the force that we know the value, we know the formula for the force balance, that is F is equal to A transpose into Y. So the so for each spring, the force balance acting upon it can be calculated as the difference between the value of the internal forces. So internal forces between the other two springs. Hence F1 is equal to Y1 minus Y2, and similarly F2 and also F3. The same will be represented here in the form of the matrices here. And so the stiffness matrix K will be obtained by combining the value of y is equal to C AU, and also the internal force balance formula F is equal to A transpose Y. By combining both the value, we're gonna get the value as A power A transpose C AU, which is equal to U. Here the A and the constant C and the transpose of the value of A will be considered as the stiffness matrix when it comes to the mechanical field, and hence the value of the stiffness matrix is obtained here. And yeah, so the value of the A is obtained in the first equation. We could see here the transpose of the value of A will be A transpose, and by multiplying this the value of this with the constant C1, C2, C3 and as well as C4, so the final value of the K is obtained like this. Yeah. And so far we have calculated the stiffness matrix for the spring which has two fixed end. The similar fashion it follows for the fixed end as well as the free end. So as we know, for the fixed end as well as the free end, since we had considered three springs for it, the value for this the stiffness or the spring constant for this value of spring 4 will be considered as 0. So hence the matrix will be reduced to 3 cross 3. The value of the value of the matrix A will remain the same, and the transpose of the value will be considered the same thing. By multiplying these three matrices, we're gonna get the value for the fixed end as well as the free end. And the another one use case of springs and its masses is when both the ends are free, that is both the ends are not connected. So if the both the ends are not connected, then the elongation at the last two ends will be considered as 0. Hence the elongation will be acted only on the spring E1 and as well as E2. The stiffness matrix for the value here will be singular, as the value of E will be 0. The determinant value of the K will also be 0. Hence the K is considered as a singular matrix here. So elongation, since the elongation will be obtained only for the two springs, the value will be obtained for the E1 as U2 minus U1, and similarly for E2, that is U3 minus U2. The matrix here 3 cross 3 will be also reduced to 2 cross 3 here, and the value for the U1, U2 and U3 is obtained here. Since the value of K is singular, the elongation will also be 0. Hence the string will feel no stretching here. The value whatever obtained in the first equation, that is minus 1 1 0 0 minus 1 1 will be transposed, hence the A transpose will be obtained, and the string C2 and C3 will obtain the spring 2 and 3, since it obtain the force of the elongation. The spring constant will only apply to the spring 2 and 3. Hence by multiplying all these three values, we gonna get the value as C2 minus C2 0 minus C2 C2 plus C3 C3 0 minus C3 and C3. So this as the stiffness matrix for the spring which has free ends. And next comes the circle of springs. So the circle of springs is obtained when the in case of three spring, when the third spring has been connected back to the mass of the first spring. So this since by connecting all those three springs, this doesn't make the k as invertible. And since the forces has been acted equally upon it, the value of the k will be singular, hence the determinant value will be 0 here. So here we have considered the a and a transpose and as well as the value of a. By multiplying it, we're gonna get the value of 2 minus 1 minus 1 and minus 1 2 minus 1 minus 1 minus 1 and as well as 2. So in this way, by considering the three formulas, that is AE is equal to AU, Y is equal to CE, and also F is equal to A transpose Y, we could calculate the value for the stiffness matrix in the three way. Hence, the conversion of the uh, equation to the vector form is thus obtained. So next, the example will be conducted by Mohit. Thank you.
Yeah, so I will explain the examples. So let's consider this example where we have one end as free and another end as fixed. So we are given that C1, C2, C3 value are 1. So by this, if we put the values, we will get the C matrix as identity. We can see the entry in K1 is 1 instead of 2 because the bottom spring is free. So it will have only one connection to the upper mass. So let's suppose all the masses are m. So generally the formula for like distance into the stiffness matrix is equal to force. So to calculate the distance, we can take the inverse of the stiffness matrix into the force. So by calculating the inverse of the stiffness matrix, we will get this particular matrix. And so if we solve this matrix, we will get this particular mg by c into 356. So this value 356 shows that the answer is what we are getting is expected because the upper mass uh, like the number 3 appears in the U1 because all the three masses are pulling that first spring. The next spring moves by the distance moved by the first spring plus the distance moved by the other two. So that's why it's 5. And the third one is the most elongated. So its value is 6. Similarly, if we calculate the elongation at every spring, we can see the numbers we are getting is 3, 2, 1. So this shows that as the force was maximum at the string which was at a fixed end, so we are getting a coefficient of 3 in the as at that place and 1 at the lowest where there is one end free. So the elongation is the least. Next, Nitin will explain about the differential equation. Then I will again explain. Nitin.
Yes. Am I audible? Hello. Am I
Yeah,
audible?
you are audible. You are audible.
So as my teammate already explained, that engineering mathematics is applicable in our day-to-day activities. Maths have a long history of application in solving linear equations. Maths applies to several branches of science as well as different mathematical disciplines. We can see the result of matrix in every computer generated image that has a reflection or distortion effect, such as light passing through a rippling water. Before computer graphics, the science of optics uses matrix to account for reflection and for refraction. In mathematics, one application of matrix notation supports graph theory. In an adjacency matrix, the integer value of each element indicates how many connections a particular node has. As we use matrix in mathematics as and engineering because often we need to deal with several variables at once. Example, the condition The coordinate of a point in the plane are written x comma y or in space as x comma y comma z, and these are often written as column matrix in the form as shown below. Our best example comes from mechanical, civil, and aeronautical engineering, where K is the stiffness matrix and K inverse of F is the structure response to force F from outside. Engineering leads to linear algebra in two ways, directly and indirectly. In the direct way, the physical problem has only a finite number of pieces. The laws connecting this position or velocity are linear. The laws are expressed by matrix equation. The second way is the indirect way. The physical system is continuous. Instead of individual masses, the masses density and the force and the velocities are function of x or x comma y or x comma y comma z. The laws are expressed by differential equations. Can you move to the next slide? So, here I'm going to explain how we are going to convert differential equation to matrix equation using an example. Uh, Mohit, one slide back. Uh, So the basic example we are going to take is minus d square u by dx square, which is equal to fx. As we know, differential equation are continuous and matrix equation are discrete. The basic example what we have taken above can be written also as k naught u is equal to f, where k naught is the stiffness constant and f is the force. The steps from second derivative to second differences are used. First, we will start with the fixed boundary condition at both ends x is equal to 0 and x is equal to 1. The fixed point boundary problem can be written as next slide minus d square u by dx square is equal to 1 with u of 0 is equal to 0 and u of 1 is equal to 0. The above differential equation is linear. A partial solution that we can derive for it is written as u of p is equal to half of x square. Then we know d square u by dx square is equal to minus 1. We can add any function in this null space. Instead of solving for a of x is equal to 0 for a vector x, we will solve minus d square u by dx square which is equal to 0 for a function u of n of x. Next slide please. So the null space solution is un of x is equal to c plus d of x, where c and d are the variables we have to find. And the complete solution can be written as u of p plus u of n. Now we will find the value of c and d from the boundary condition which I said earlier. So we are going to set the value of x is equal to 0 and then x is equal to 1. At x is equal to 0, u of 0 will become 0 and it forces the value of c to be equal to 0. And at x is equal to 1, u of 1 is equal to 0, which forces the value of d to become half. Uh, then for d is equal to 1 by 2, we will get the final solution as u of x is equal to half of x square plus 1 by 2 of x, which is equal to 1 by 2 taking common and x minus x square. This solves the fixed boundary value problem. To get matrix instead of derivatives, we have three basic choices. Either we can use forward or backward or central differences. To change the solution to matrix form, first we have to replace the derivative in minus d by dx of du by dx is equal to 1 by forward and backward differences. Our matrix equation for n is equal to 3 and delta x is equal to 1 by 4 look like this. It is nothing but 1 by delta x square and the two difference matrix and the displacement matrix which is equal to 1 1 1. Here, can we go to the next slide? Here the two first differences are transpose of each other. The equation is A transpose A of u which is equal to delta x square of f, which was previously explained by Pratiksha. When we multiply A transpose of A, we get positive definite second difference matrix K, which is nothing but K naught U, which is equal to delta x square of f, which can be written as 2 minus 2 0 minus 1 2 minus 1 0 minus 1 2 u1 multiplied by u1 u2 u3 is equal to 1 by 6 of 1 1 1. Then we will get the value of u1 u2 u3 by taking 1 divided by 32 as common, and we will get a vector as 3 4 3. So the three numbers u1, u2, u3 are exactly correct as the true solution of the equation which we got previously. That is nothing but u is equal to 1 by 2, taking common from x minus x square at three different mesh points, which are nothing but x is equal to 1 by 4, 2 by 4, and 3 by 4. So below figure show the true solution and the approximations. The resultant curve is a parabola. As you can see, in the parabola, there are 3 points u1, u2, u3, which show the result we will get after solving the example we have taken. So there are two other possibilities in this kind of problem. The first possibility is the end x is equal to 1 is free. There is no support at that end. This is an example of a hanging bar is fixed only at the top. There is no force at the free end x is equal to 1. The translation du by dx is equal to 0 instead of the fixed condition u is equal to 0 at x is equal to 1. The other chance is in the coefficient c of x is equal to 1 by. The stiffness of the bar n is equal to bar is varying. We go from x is equal to 0 to x is equal to 1. Therefore, C of x will become diagonal matrix C, which is multiplied by 1 plus delta x up to 1 plus 4 delta x at the mesh points. The matrix K is equal to A transpose C of A will be symmetrical and positive. Therefore, the fixed matrix is written as A transpose of A and A transpose C of A. It was previously explained, Pratiksha, that with the help of this we can get the stiffness constant K. Now further Mohit will explain.
Hello, good evening once again. So like there might be some people wondering like we are giving presentation on the application of engineering. Still, mostly we are not able to relate because most of the things here are theoretical. So I will try to bring them some like real life examples. So if we look around, we will find that the matrix has application in almost like mostly too much fields like electronics, image processing, computer graphics, quantum mechanics, probability, statistics, economics, many more. So if we look at this particular, so this is a vector. So if we multiply with matrix, we will get this output vector. So so it's nothing that we are just applying a rotation matrix to it, and then we are applying a scaling matrix. So you can see here this black line, so it's a vector. So if we apply a scaling matrix, we will get this red one. If we apply a rotation, we will get this. So similarly, by changing the value of the rotation matrix, we will get this, and similarly the scaling. So so coming to this example, so let's say these four blue lines, they are some particular vectors, and we are applying a particular matrix to it. So we are getting this red ones as a resultant. This blue one is getting on the same line. It's just scaling this matrix. It's not doing any rotation. It's just scaling this particular vector. Uh, Wait, sorry. Uh, yeah, so as we can see, if we like change the value of the vector at the same, like just increase the length, and if we apply the same matrix, we will get the same similar red line matrix. Just the scaling part will increase. So now take a look at this particular blue line. So as we can see, after changing the value also and applying the matrix, we are seeing the final matrix is coming on the same line only. So this particular vector is a eigenvector of that particular matrix. So of eigenvector is very useful, which can be used as a lot in different application. So let's consider this particular example. Let's think of a isolated world where there are few people restricted. So currently few of them have become zombies. So at a rate there are currently 150 humans and 150 zombies. So in an hour at a rate of 20% humans are turning into zombies, and there is some medicine something is going on which is turning it back to human. So at a rate of 10% the humans are turning the zombies are turning back to human. So now the question arises, what will happen in the long run to the number of humans and the number of zombies? So if we take a look, so let's say the first hour point, so uh, by 0.2% the humans were turning to zombies, so 0.8% of human will remain as human, and 0.1% of zombies are turning back to humans. So totally we will get 135 humans after 1 hour. Similarly for zombies, 0.2% of human will turn to zombies, and the 0.9% of the existing will remain. So we will get 165 as zombie. Similarly, if we apply for the next hour, we will get this one humans as 125 and zombies as 175. So this we can represent it in the form of a Markov matrix. So the property of a Markov matrix is there is no negative value here, and the sum of these two should come to 1. So zero point 0.8 plus zero point 0.2 is 1. Similarly, so these type of matrix, we can solve this type of question using this matrix. So if we put x and y here, similarly x and y here, and solve for a constant x and y which we want to get in the long run, we will get human as 100 and zombies as 200. So if we put 100 and 200 in this particular equation, we will get 0.8 into 100, that is 80, plus 0.2 into 200, that is 20. So 100 here, and similarly if we solve zombie we will get 200. So after a particular time, every hour, the numbers will try to converge at that particular point, that is humans equal to 100 and zombies equal to 200. So similarly, there is another example. So this particular image is about a Roy that belongs to 1992 Los Angeles Roy. So there is this truck driver named Regal Denny. So there is this Wikipedia link, if you want you can read about this. So as you can see, this is the quality of image which was captured from the camera which was present at the traffic. So as you can see, we are not able to see clearly who this person is beating, and so we can't identify this person. So now using the application of DIP, they were able to identify this person. So I will explain how. So let's consider this image. So image is nothing but a mixture of pixel. So let's see this example. So here you can see this particular image. It's a mixture of many pixels combined together. So at a particular every pixel is a is nothing but a matrix. So if we multiply this with a kernel, so this is a smooth kernel. So if we multiply this, it will blur this image. So let's say we will take any point and we will multiply this value, and we will take the average at that particular point. So as we can see, for this particular point, all these near points are 1. So we will get 1 here, and similarly 1 here. But for these points, we will get this particular value, this particular value. So it will keep changing. So if we now convert it back to color, we will get this kind of image. So this is blurring of image. Similarly, we can use different kernels to sharpen the image and also to detect edge. So let's say these values, these are all positive. If we want to sharpen it, so we will make this value as large and the less value as negative. And if you want to detect an edge, then the sum of the negative value should be equal to the sum of the positive value, so that overall the sum should become 0. So like this particular example, so here we can see the sum of -1. These are 8 columns, so it will be total -8. This 8. So if we apply this particular kernel to this image, as explained before, we will get this particular image. So it will detect the edge of this particular image. So similarly, if we apply the edge detection to this particular image, we will get this as a edge detection. So here you can see this particular thing. So actually this particular image, it's a enhanced version of this particular arm of this person. So as we can see, there is this edge which shows a particular type of tattoo which was very famous at that time in a gang. So using this tattoo, this person's gang identity was able to identify, and he was identified as a Damien Villian, who was part of a gang named LA4. So using this picture only and the tattoos, the jury presented and held him like culprit. So these are the few examples which we can find in real life of matrices. And thank you. That's from our side.
Hello.
Yes, ma'am.
Anybody have a question? Those are participants. Please free to feel and then ask the question. They are ready to answer. Yeah, we have to give. Anybody have a question? Yes, Vaishnavi?
No, ma'am.
Anybody, those are joining class, free to ask the question. Okay. Yeah. Gunavati?
Ma'am, I'm not
Yeah.
getting the chat box to share the feedback link here.
Yeah.
Can I share it with you, ma'am? Can you post it in the
Yeah,
chat
I'm
group?
also logging in the mobile only.
Okay.
You share it. Yeah, I'm also in the login mobile because you know that no late for that joining the webinar. If I what we can do, we are going to share it in the group.
Okay, ma'am. We'll
What
share
about
in
our
the group
webinar?
only, ma'am. Because I could not
Yeah.
able to put the chat box here.
Yeah, yeah. Better you share it
Oh,
link. I'm going to share it in
okay.
webinar there and also our class team. And then we know
And
that
the
how many
webinar
are there.
group, I will put it.
Generate,
Yes, ma'am.
please generate attendance. That's all.
Yes, ma'am. That I'll do it, ma'am.
Okay.
Okay, ma'am.
Yeah. Anybody? Okay. Anybody have a question? Yeah. Thank you very much for Mohit Kumar and then name I've forgotten. Hello.
Nitin, ma'am.
What's another one? Hello.
Nitin.
Please unmute and tell me your name.
Ma'am, my name is Nitin.
Hello.
Nitin, ma'am.
Hello.
Hello, ma'am.
Ma'am, Nitin.
I'm not audible. Hello.
Ma'am, you are audible, ma'am. I think some network issue for you, I hope.
Yeah, I'm audible.
Yes, ma'am.
Yeah. Please unmute Mohit Kumar. What's another one name? Hello.
Nitin Priyadarshi.
Nitin Priyadarshini and also Pratiksha. In absence, sir, she explained very nicely through record. Thank you very much once again from all the participant side and associate dean Dr. Gunavati and also me. Thank you very much. In a busy schedule, you are explained. I know matrices in engineering, you don't have much, you don't get much thing in any textbook and Google search. Based on that, you explain very nicely. You please on camera, everyone. We are that is also record because we need a photo for to prepare a report. Pramod, Meghana, And then Murali, Yuvika, please open open. Yeah, on your video, everyone, please. Hello. All participants also, I'm requesting you please on your video. Vaishnavi. Yeah.
Yes, ma'am.
Everyone, please, those are login today class, including participants, are requesting everyone please on the video. Because we need photo for that. That is also recording, no? That's fine. Pramod? Anybody log in your laptop? Meghana is login laptop.
Even I am.
Yeah, please take a photo, picture for this. Hello?
I'm taking.
Yeah. Where is Meghana? Everyone joined or not?
Yes, ma'am. I'm here only. I've switched on my camera.
Yeah, now. Because I'm logging in my mobile, no, I couldn't able to see all at a time. Madam is still in the college only, I think. Yes, ma'am?
In the bus now.
Boss. Okay.
Ma'am, is any student capturing this? Because
Yeah, I
cannot.
told Pramod, you take her, na?
Okay.
Yes,
And
ma'am.
also I have to stop recording also, ma'am. Or after this.
Yeah, please take photo. Photo ತಗೊಂಡ್ಯಪ್ಪ.
Ma'am, ತಗೊಂಡೆ.
ಮೇಘನ ನೀನು ತಗೊಮ್ಮ ಒಂಚೂರು ಯಾರು